welcome to Calculus 1, where we will be taking a look at limits and how they work. What is the standard form of a limit? Well, we're talking about a number approaching a value that doesn't necessarily exist, but it is approaching a value. It's not that value at that point, but it exists. That's the standard form. The limits of rational functions, well, it's a function over another function, and we can evaluate the limit like this. All right, so I set out some practice problems here. And as we go through them, we will discover what evaluating a limit and limits actually mean. So let's start. So we'll start by letting f of x equal to x squared plus 5x plus 9. And as x approaches infinity, what does f of x approach? So try drawing the general shape of the graph. So let's see, what is part A giving us? Express the problem prompt in terms of limit notation. Okay, well, as we saw here, we have the limit as x approaches some number, right? Well, infinity is a concept, but it's okay. So as x approaches infinity, we'll always write the limit operator, which is the letters lim, and x, which is going to be our variable, right? Because it's saying as x approaches, it will approach infinity of x squared plus 5x plus 9, okay? Now let's evaluate the limit. So let's look at the general shape of the graph like it tells us. So this would be my trusty graph. So this is a quadratic function, and it's going to be opening upward. So it's going to look like this. Maybe a little more U-shaped like that, and touching the origin, right? We can move this down a little, make it more accurate, right? So as we go towards infinity, positive infinity is that direction. So it's going to be also positive infinity up here. So our answer will be positive infinity. Now, what if I asked you what was the limit of the same function? Let's say 3 here, of x squared plus 5x plus 9. It's actually a lot easier than doing infinity, because all you have to do here is plug in the number 3, because a polynomial is continuous everywhere, and we can prove that later on. So this is equal to 3 squared plus 5 times 3 plus 9, which is equal to, well, 3 squared is 9, plus 5 times 3 is 15, plus another 9 is just 9. And we can add these together. So 9 plus 15 is 24, and 24 plus 9 is equal to 33. So that is the limit as x approaches 3. And this works generally for continuous functions at that point. However, indeterminate form is 0 over 0, which we'll see here if we try the same approach on number 2. We'll start with number 3. We're going to try to plug it in. Okay, so let's try plugging 0. So we'll do cosine of 0 minus 1 times divided by sine of 0. Cosine of 0 is equal to 1, and 1 minus 1 is 0. Sine of 0 is 0, which gets us 0 over 0. And like I said up here, when we have indeterminate form, we know that something is wrong and we cannot just straight plug it in, because at 0, there's no defined function value. And so just like what I meant here, where there must be a defined function value in order to just plug it in. Therefore, we must do some algebra to get a defined answer. So let's start using our trigonometric identities to try to solve this. So I'm going to do the same thing by multiplying the conjugate of whatever this is. So I'm going to change the sign in the middle. Right, so I'm multiplying it by plus 1. And I must do the same thing to the bottom. Okay, so this will give us, right, we get cosine times cosine is cosine squared. So actually, let's rewrite the limit first. So you get cosine squared, right, and we know that it's going to be minus cosine of x, then plus cosine of x, which just cancels out because minus and a plus with the same number or the same expression will cancel out, then minus 1. And I don't want to do anything to the bottom. And if you notice a pattern, a lot of these things, you don't need to do a lot of stuff to the bottom. So the top looks familiar, looks like a familiar identity. It looks at the Pythagorean identity. So it's sine, which is sine squared, plus cosine squared is equal to 1. We can somehow manipulate, we can manipulate this expression to get something like that expression. So I'm going to do cosine, I'm going to subtract 1 on both sides, minus 1, right? So I'm moving that sign there, the minus 1 there. I'm going to add plus sine squared is equal to 0, right? And then I'm going to move the sine squared over. So it's cosine squared minus 1 is equal to negative sine squared. And now I have something actually exactly the same as that, and I can plug it in. So let's move this out of the way so we have more room to solve the problem. And I have limit as x approaches 0 of now negative sine squared of x over sine of x times cosine of x plus 1. And now since I have sine of x is on outside, this can cross out, and that one will, and only one sine of x will cross out, and we have just minus sine of x. Now, this is technically a negative 1 that is multiplying the sine of x. So we can also take any number out of the limit because the limit operator is what we call linear. So we can always take a number out. So for example, if you have limit as x approaches some number c of k of f of x, and k is a constant, this is also equal to k limit x approaches c of f of x. So we can do the same thing here. So we get minus the limit as x approaches 0 of sine of x divided by cosine of x plus 1. Now, what happens when we try to plug it in, we try to plug 0 in for this expression? Well, we get minus sine of 0 divided by cosine of 0, which is 1, plus 1. And sine of 0 is 0, and since 0 is on the numerator, we're not dividing by 0, and therefore this limit is 0. And this is a new property that we discovered of the limit operator. Okay, moving on. What is limit as x approaches infinity? Well, 4x cubed plus 3x squared plus x divided by 8x cubed plus 3. At first glance, it doesn't look very friendly. However, there are a couple tricks that we can use, one advanced and one not. One called L'Hopital's rule, which we'll learn sooner rather than later. Rule. And the shortcut, which you will be taught now. Shortcut. Okay? So whenever we have a infinity, any type of infinity, negative infinity, positive infinity right here, in order to find this limit, we'll take the ratio of both leading coefficients, okay? And in order to do that, the leading exponent must be the same. So we see we have a 3 here, a cubed, and a cube here. You can take the ratio of them. So this is equal to 4 divided by 8, which is also equal to 1/2. So that will do it as well. You can skip a little long in the video later, but I'm going to show you how we can use L'Hopital's rule right now. We know So L'Hopital's rule says if we actually we'll get to that later. Okay, so limit, and so on the next one, you have limit as x approaches negative infinity, 2x cubed plus 8x divided by 8x plus 3. Okay, this is the same sort of thing here, but we see that our leading our leading exponent. So for number 5, we have the limit as x approaches negative infinity of 2x cubed plus 8x divided by 8x plus 3. Well, first off, we see that the leading exponent is not the same, so we have to make them the same by adding a 0 as a coefficient. For example, we can rewrite this limit as x approaches negative infinity of 2x cubed plus 8x divided by 0x cubed plus 0x squared plus 8x plus 3. And as you know, anything times 0 is 0. So this doesn't change the value of the expression. Now we can take the quotient of the two leading coefficients. It's going to be 2 divided by 0. Anything divided by 0 is an error, so this is infinity. Okay? Or we can also say undefined. Okay. Is function continuous at x equals 1? What is the definition of continuity? Well, the definition of continuity is as the limit, and this is a good time to introduce, so the limit as c in the right of f of x, so this is a good time to introduce what is a one-sided limit, so equals limit as x approaches c minus 1 from of f of x, and this also must equal f of c. Okay. Now, what are the minus signs and the plus signs that look like exponents on the what x is approaching? Well, let's look at a graph, okay? And let's just say it's absolute value, just as an example. When we're saying when plus sign, it's approaching from the right, so the x is decreasing towards our value. Remember we said it's approaching, not necessarily getting at the value, but it's approaching. So let's say if it's approaching, let's say -1 right here, it's going from the right, it's going to point towards the left because it's coming from the right. It's going to point and get infinitely close to 0. And from when you come from the top, it's going to go from the top, and from the top from the left, which is the minus sign, it's going to get closer to the point from the left. So that's what I mean by left and right hand limits. Okay, so let's try to test this example. What about 8? Is this function continuous at x is equal to 1? Well, here we're given a piecewise function. So let's try, and I'll leave the graph of it on the right as well. And when you try to approach it from the left, right, and we approach it from the right, we know that this is going to be approaching from the left, and this is going to be approaching from the right. So if we can do the same sort of thing, and if we can, let's first perform g of 1. Well, for the piecewise function, we were told that this is equal to 1 as well. So 1 squared minus 1, we'll actually write it down here, 1 squared minus 1 is equal to 0. And so in order for this to be continuous, the limit must exist, and the limit must exist and both sides must equal to 0, one implying the other. Okay, so we'll do the limit as x approaches 1 minus, right, from the left, it's going to be x squared minus 1. And does this equal the limit at x approaches 1 plus for tangent of minus pi of x over 8? Well, we know that this is going to be 0, right? This will be 0. And the other side, I know that will not be equal to 0 because tangent of negative pi over 8 is not 0. It's only 0 when x is equal to 0. Or or pi. So this does not equal 0. So 0 does not equal not 0. We don't have to evaluate it, but we know it's not 0. Therefore, this isn't continuous at x is equal to 1. Okay, so this is our conclusion. Okay, so recap, we learned that we learned about what the standard form of a limit is, what is a rational function, what does it mean to approach a number, meaning it gets infinitely close to the number but not quite there, and how to evaluate a limit, and some rules and some tactics to tackle them. And we also learned about continuity. I hope this helped, and thanks for watching.